Hello and welcome to Chapter 6 on the formation of the solar system, which in addition to talking about how our particular solar system was formed, is also going to talk about the NICE model and how solar systems in general are believed to be formed now. The NICE model is a model that was developed in Nice, France, and it's a computer model which details what we think happened with the formation of the solar system given a number of different variables that we placed in. It was replaced or updated with the NICE 2 model, which is what we're going to go over. Some chemical evidence in space debris that we have analyzed on Earth suggests that the dense core in which our solar system formed may have become genes unstable when its gas and dust were hit by the shock wave from a supernova. We call that dense core the solar nebula, also called the protosolar or presolar nebula. The solar nebula initially had a diameter of at least 1,000 AU, or astronomical units, 1,000 times the average distance from the Earth to the Sun, and a total mass of about 2 to 3 times the solar system's present mass. At first, that nebula was a very cold collection of gas and dust, well below the freezing point of water. Although most of the solar elements was hydrogen and helium, ice and ice-coated dust grains composed of heavier elements, metals, were scattered across this vast volume. Deep inside the nebula, gravitational interaction caused gas and dust particles to rapidly fall towards its center. In terms of the physics presented in Chapter 2, the cloud's gravitational potential energy was being converted into kinetic energy, energy of motion. As a result, the innumerable collisions there, the density, pressure, and temperature of the center of the nebula began to increase, producing a concentration of matter called the protosun. As the protosun continued to contract, become denser, and to increase in mass, atoms within it collided with increasing speed and frequency. This activity created growing pressure inside the protosun, which in turn caused its contraction to slow dramatically. Such collisions also created heat, causing the protosun's temperature to soar. Therefore, the first heat and light emitted to our sun came from colliding gas, not from the thermonuclear fusion as it does today. At the same time, there was also considerable activity in the outer regions of the disk. Rotation plays a key role in the formation of the solar system. When it first developed, the solar nebula was a very slowly rotating ensemble of particles. Recall from Chapter 5 that this rotation occurred because the formation of interstellar clouds is turbulent. So these clouds are created with many slowly swirling regions. As a result of this motion, the solar nebula created from one of these eddies had angular momentum. Because angular momentum is conserved, rotating matter spiraling inward in the young solar nebula revolved faster and faster, like the skater mentioned in Chapter 2 when she pulls her arm waves in. This motion had the effect of flattening the nebula into a disk. You can see an analogous effect of rotation in the way the ice skater's dress in the figure is forced into a plane as she spins. Had the solar nebula been non-rotating, it would have been essentially spherical and collapsed en masse to create a star without any planets or other orbiting matter. Even the debris in this inner solar nebula that formed the protosun was orbiting as it fell inwards, like water spiraling before it goes down the drain. Therefore, the protosun was spinning and the sun that formed from it rotates. The outer region of the young solar nebula was probably very ragged, but mathematical studies show that the combined effects of gravity, collision, and rotation terraform even an irregular dense core into a rotating disk with a warm center and a cold outer edge about 30 AU from the protosun. Eventually, the gas and dust in this disk, the solar nebula, were orbiting fast enough to stop spiraling inwards. As occurs with all gases, the protosun's temperature increases as it became denser. As the protosun radiated more and more heat, the temperature around it began to increase. The protosun's increasing temperature vaporized all common icy substance, including carbon dioxide, water, methane, and ammonia, and the inner region of the disk. These gases then blew away, along with the abundant hydrogen and helium gases that also existed there. Metal-rich dust particles, which are not easily vaporized or blown away, remain throughout the disk, including in their inner region. Within 100,000 years or so, the disk forming no gases or ices orbiting closer than roughly 3 AU between what are now the orbits of Mars and Jupiter. Temperature were low enough beyond this distance that gases, primarily hydrogen and helium, and ices remained in orbit around the protosun along with the dust particles out there. The boundary beyond which these gases and ices and water, carbon dioxide, methane, and ammonia persisted is called the snow line, or the frost line, or the ice line. Within a million years of when the gene's instability occurred, the solar system had differentiated into an inner region containing just metal-rich dust grains and an outer region also rich in hydrogen gas, helium gas, and ice-covered dust particles. Neighboring dust grains beyond the snow line began collecting with each other. The early motion of this debris was very chaotic. Many of these collisions caused dust grains to grow, while many other collisions broke apart larger pieces of the debris. When dust particles finally reached sizes of a few millimeters, they began plowing through the surrounding gas. As the dust particles pushed aside this gas, the gas took energy away from the dust particles, which slowed them down as much as you slow down when walking into a headwind. As a result of the losing energy slowing down, this dust, still feeling the gravitational attraction of the protosun, spiraled inward toward it. The gas that was struck in this process was sent outwards. The collision and acceleration, the coming together of smaller pieces of matter to form larger ones of dust particles, continued as they spiraled inwards. Like static clinging between closed, accretion of dust-sized particles is due to the attraction of their charged particles, protons and electrons, while accretion of much larger pieces of debris is primarily due to their mutual gravitational attraction. Through accretion, the dust grew into pieces of debris meters across. Calculations show that pieces of debris meter across could have spiraled inward to half of its original distance from the protosun in just 1,000 years. Collisions destroyed some of these bigger bodies, while some of them merged and grew even longer. Eventually, a few billion of these boulders reached dimensions of a kilometer or so, large enough for their mutual gravitational attractions to enhance the rate at which they collided. Such pieces of debris are called planetesimals. The formation of planetesimals that had migrated inside the snow line was a turning point in the young solar system's evolution. They collided with countless dust particles as well as with each other. Sometimes colliding planetesimals destroyed each other and returned to dust. Eventually, however, these collisions led to the growth of several hundred substantial bodies that persisted and eventually reached the size and mass of our moon. At this size, the gravitational attraction of the planetesimals was strong enough for them to either sweep up the surrounding rubble or to fling it far away, thereby clearing out nearby space and limiting their own growth. These bodies led to the formation of the terrestrial planets, to which we will return shortly. This is shown in this diagram, where the planet protostar begins spinning, begins accumulating protoplanets and planetesimals around it, and these planetesimals eventually become terrestrial planets. We begin our exploration of the individual planets which were created with Jupiter, which was the first gas giant and was the first planet created. Many planetesimals that formed out beyond the snow line remained out there in substantially non-circular orbits. Because it was so cold, these planetesimals collected large quantities of hydrogen and helium as well as metals. As a result of their high elliptical orbit, they crossed paths and many of them collided and merged with each other, thereby creating larger bodies. One planetesimal located about 0.5 AU beyond the snow line accreted enough of its companions so that it had perhaps 15 Earth masses of rock and metal. With only a few thousand years of beginning of the accretion process, it grew into the planet Jupiter. The impacts heated the growing protoplanet, but Jupiter never became a star because its total mass is too low for its compress and heat its core enough to enable hydrogen fusion, such as occurs in the Earth's core, to commence. Indeed, Jupiter would need to be about 75 times more massive for it to sustain core fusion and therefore be classified as a star. A few million years after Jupiter formed, collisions of planetesimals led to the formation of a second rocky world of about 10 Earth masses located a few astronomical units beyond Jupiter. This second world underwent the same process of accreting hydrogen, helium, and ice, thereby creating Saturn. By the time Saturn formed, however, a lot of the gas in its vicinity had already been stirred up and dissipated by Jupiter, leaving Saturn with less matter to accrete. During all this time, the two young planets were also gravitationally interacting with each other. This tug-of-war transferred energy between the two planets, eventually causing both of them to stop spiraling inward and start spiraling back out until Jupiter arrived at its present location with Saturn farther out. This change from spiraling inward to spiraling outward is called grand-tack, in that it is analogous to a sailboat changing direction to move upwind. The gravitational effects of Jupiter and Saturn forced many planetesimals to become concentrated out beyond Saturn's orbit, leading to the formation of Neptune and Uranus. The debris that was far from the protosun had been spiraling inward for several million years before they formed. Thus, these two planets are believed to have formed substantially closer to Saturn than they are today. Furthermore, computer simulations suggest that at the time of their formation, Neptune was closer to the protosun than Uranus, the opposite of their positions now. While the planetesimals that formed Neptune and Uranus were rich in hard water, they formed so late that Jupiter and Saturn had dissipated most of the hydrogen and helium in their neighborhoods. Therefore, Neptune and Uranus have a substantial amount of water, along with carbon dioxide, methane, and ammonia, generically called ices. But each contains only a couple of Earth masses of hydrogen and helium. While Jupiter and Saturn are called gas giants, Neptune and Uranus are called ice giants. These four planets are all outside of the ice belt and the asteroid belt and are thus called the outer planets. The inner planets, Mercury, Venus, Earth, and Mars, formed as a result of collisions between planetesimals that were mostly composed of heavier elements or metals. Within 100,000 years of the dust beginning to coalesce and to spiral inward, as described above, bodies with 0.1 Earth masses were able to form in it and collide with each other inside the snow line. These planetesimals likely formed in relative circular orbits and then collided to build their planets in relatively circular orbits. Whether the inner planets formed in orbits near their present average distances from the Sun, or whether they migrated like the planetesimals outside the snow line that formed the four giant planets described above, is presently under study. In the end, however, the collections of hundreds of moon-sized moon-sized planetesimals led to the existence of four rocky inner planets: Mercury, Venus, Earth, and Mars. We are literally made of stardust. Because these planets were located inside the snow line, they did not acquire coatings of hydrogen and helium like those we still found in the giant planets today. However, enough hydrogen and helium were part of the debris that formed the inner four planets that these gases became their first atmospheres. Being so light, these gases quickly drifted into space. The large quantities of water that exist on Earth today, that existed on Mars, and that is likely to have existed on Venus came in part from ices in the planetesimals that created these worlds, and in part from impacts of water-rich comets and possibly water-bearing asteroids sent inward as the giant planets were spiraling back out. One planetesimal impact on young Earth was particularly notable. It apparently was struck by a planetesimal that has been named Theia, which has a mass of roughly that of Mars. Computer simulations of such an impact indicate that it would have splashed a lot of degrees off Earth's surface and into orbit, at the same time tilting Earth's rotation axis. This event is believed to have occurred about 4.5 billion years ago, within 100 million years after Earth started forming. The orbiting debris created a short-lived ring which clumped together in a process analogous to how planetesimals grew from collisions and formed our moon. The outward flying planetesimals spread way beyond the original disk, which had a radius of 30 AU as noted above. Millions of them were flung into a bagel-shaped volume beyond the orbit of Neptune that is now called the Kuiper Belt, named after Gerard Kuiper, who first proposed the existence of such a region in 1951. Many more planetesimals were sent out even further than the Kuiper Belt, creating a spherical distribution of debris called the Oort cloud after Jan Oort. Kuiper Belt objects, or KBOs, were first observed in 1992. There are two families of KBOs, most of them comprising one family, are in relatively circular orbits, orbiting in planes close to the ecliptic. These are called cubewanos after the first one discovered and named. A growing number of pairs of these KBOs have been observed to be orbiting each other. They are binary pairs, or KBOs. These KBOs probably formed at the same time as the inner bodies of the solar system. The other family of KBOs was probably formed in the solar system and was sent outward by gravitational force from the various planets. Many of them have orbital planes farther from the ecliptic, and they have more elliptical orbits than the cubewanos. Because of their elliptical orbits, and possibly because of collision or near misses between them, some of the outer KBOs enter the inner solar system today. When this happens, the sun's radiation vaporizes some of their ices, producing the long flowing trails that we associate with comets. Now we turn to the major reservoir of leftover rock and metal debris remaining from the inner solar system, the asteroid belt. Located between Mars and Jupiter, orbiting in this region are millions of planetesimals and smaller pieces of debris. The total mass of debris in the asteroid belt is about that of our moon's mass, much less than the mass of a planet. But there were more bodies in the asteroid belt in the distant past, but impacts and the gravitational tug of Jupiter pulled many of them away and kept the remaining debris spread out, thereby preventing it from ever coming close to forming a single larger body. About 4.1 billion years ago, NEAS model computer simulations suggest that the impact rate skyrocketed as planetesimals in the asteroid belt and possibly the Kuiper Belt were pulled toward the inner solar system by the giant planets that were readjusting their orbits under the influence of their mutual gravity. Numerous asteroids were pulled into orbits that crossed the paths of the inner planets in our moon. If these simulations are borne out by evidence from the moon and space debris, then at the time the solar system entered a period called the Late Heavy Bombardment, in which the inner planets in our moon were pounded by myriad impacts. This period ending as the errant asteroids were destroyed by striking something, by falling into the sun, or by eventually being flung out of the inner solar system. Mercury, which is particularly dense when compared to the other inner planets, may have lost much of its lower density outer layers in a collision that occurred during this time. According to the most recent accepted definition, a planet is a celestial body that 1. Orbits the sun or another star, 2. Has enough mass so that its own gravitational attraction causes it to be essentially spherical rather than being a large irregular rock in space, and 3. Has enough gravitational attraction to clear its neighbors of other orbiting debris. Planets clear their neighbors by either pulling surrounding debris onto themselves or flinging debris far away from their orbits. There are thus 8 known planets in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. A dwarf planet satisfies conditions 1 and 2, but not condition 3. These objects are smaller than planets, hence with less mass and less gravitational attraction. This definition is the reason that Pluto was demoted from planet status. So far, of the myriad candidate bodies, astronomers have agreed on 5 dwarf planets: Pluto, Ceres, Haumea, Makemake, and Eris, with several other bodies being considered for that classification. A moon, or natural satellite, is an object orbiting a larger body that is in turn orbiting the sun or another star. Rings of billions of dust particles and mountain-sized pieces of debris in orbit around Jupiter, Saturn, Uranus, and Neptune are yet another category of solar system object. Everything in the solar system that is not a planet, dwarf planet, moon, or part of a ring system is called a small solar system body, or SSB, not Super Smash Bros. Brawl. The tricky part of the classification system for objects in the solar system is that several classes overlap. For example, the largest asteroids are dwarf planets, whereas the vast majority of asteroids, as well as all meteoroids and all comets, are small solar system bodies. These classifications are laid out in this diagram. It is also worth noting that most of these planets are within a few degrees of the ecliptic and also have fairly circular orbits rather than more eccentric elliptical orbits. During the 100 million years that the inner planets were completing their formation, the protosun was also evolving. Throughout this time, the temperature and pressure at the center of the slowly contracting protosun continued to increase. Finally, its core reached a temperature which is hot enough to initiate hydrogen fusion, in which hydrogen is converted into helium. Such fusion generates energy in the form of gamma rays, which, slamming into the gases in the protosun, created enough pressure inside the protosun to stabilize it, here meaning preventing it from expanding or contracting. At that point, the sun became a star. As noted earlier, some of the energy generated in the sun's core leaked out, which is why the sun shines. Hydrogen fusion continues in the sun's core today, and the energy generated there over the past 4.5 billion years has maintained the sun's size and temperature, and therefore enabled Earth to sustain life. Since sun-like stars take approximately 100 million years to form a nebula and settle down, the sun probably became a few full-fledged stars around the time of the accretion of the inner planets was completed. Radiation from the sun heated and dispersed the remaining gases in the solar system, thereby helping to limit the sizes of the planets. All of which is to say, the planets started out as a disk, became planetesimals, came together, had the various gases swept away or combined into the planets and formed the planets that we see now. Like exoplanets, all of the planets have different properties, and it is somewhat tedious or clunky to compare all of them over voice, but in general, the orbits are mostly circular except for Mercury. The size has smaller terrestrial planets, which are the inner planets, big gas giants, and medium ice giants. They have different masses and different densities, with the terrestrial planets being higher than the outer planets, different spectra and chemical composition, which we can find from spectroscopy, different albedo, where an albedo is the scattering of light, and Mercury, Earth, and Mars scatter 0.37 of light or less, or have an albedo of 0.37, which is 37% of light or less, while Venus, Jupiter, Saturn, Uranus, and Neptune scatter 0.47 or 47% or more. And then moons, Mercury and Venus don't have any. Our moon is round. Other